Yeah, and while Amanda's pulling up slides, I just wanted to personally thank Amanda for helping us out. She coordinates this for California, Nevada, which is already a huge region. So stepping in after Alicia's departure has been a huge help for us. And I'm pleased that we actually have people on this webinar because we're billing it as a drought early warning system when we're the furthest thing from drought right now. I'm just going to give a quick climate update. It's no secret that it's been wet across the region. I was just lamenting to my fellow panelists that we were supposed to have hot air balloons here at Oregon State today, and we are definitely not. It's raining. I am with the Climate Impact Research Consortium. We're one of 10 NOAA RISA teams around the country. And what we do is we coordinate with stakeholders on climate adaptation and climate preparedness. And we've also partnered with NIDIS on launching the Pacific Northwest DEWS. Next slide. So I just wanted to start with the drought depiction, even though I said we're the furthest thing from drought. This is the first time that at least Oregon has been drought-free since 2011 on the U.S. Drought Monitor, and that includes the D0 abnormally dry designation. So we're not worried about drought, but the drought early warning system is also focusing on the other end of the spectrum, which is flooding, and we're seeing a lot of that, and some of our National Weather Service friends can certainly attest to that. Next slide. But going back to the beginning of the water year, there were certainly concerns about how this year would pan out. When we launched the drought early warning system in February 2016, we were coming off the worst drought in decades in the Pacific Northwest, and it took us quite a while to catch up. Last winter was wet, and this winter was super wet, but in just 6 months, we've managed to erase all these colors from the map, and it's certainly delightful for many of us. Next slide. When we look at current water year precipitation as percent of normal, really the entire Northwest has been wet going back to the beginning of the water year, which starts on October 1. And this is a tool that was developed by our colleagues at the University of Idaho, John Batsoglu and Catherine Hedgewich, funded by CERC and the Northwest Climate Hub and other partners. And it's a way to digest all this climate data and look at it in a way that doesn't make you do any of the processing. So when we look at some of the nuances of how the precip fell around the region, the Spokane area and the Palouse in Washington definitely sticks out. Southern Idaho, parts of Southern Oregon and the Southwest Oregon coast were the big winners or losers in terms of precipitation, but really the entire region was wet. There is that spot in north central Oregon near the Pendleton area. I think that's bad data because they were certainly wet as well. Next slide. This is just a neat little tool that I wanted to throw in and make you aware of. It's developed by the Southeast Regional Climate Center, and it's called their Climate Perspectives tool. And you can ask it queries of the questions you may be looking for answers to. And this is just observed days of total precip over a trace, going back to almost the beginning of the water year through Saturday. And anything with a 1 is the highest, so the most days with rain on record for that region. So we're looking in central Washington, the Yakima region, parts of eastern Oregon as well, and then up and down the Willamette Valley, Puget Sound area, top 1, 2, or 3 most days with rain. So you're certainly justified in complaining this winter. Next slide. And just briefly, I wanted to look at the last 90 days of temperature because this is important for our snowpack. And it's been above normal in Idaho and eastern Oregon. We're seeing that in the snowpack. We're seeing it melt out quickly, but luckily there was a lot there. Next slide. And again, just looking at nighttime temperatures because this does have some implications. They've been warmer than normal for the past 2 months. Next slide. I just threw in a few graphs from some stations to show just how wet this water year has been. So the blue line here for Seattle-Tacoma International Airport is this winter and this water year, the wettest now on record, the wettest start to the water year on record. The brown line is what a normal water year might look like, and the red line is the lowest or the driest start to the water year, which is famous for being the 76-77 drought. Next slide. Same sort of thing for Portland, but Portland hasn't been able to pass 1996, 1997. People who live in Portland and in the city or in Oregon may remember that as a year with a lot of flooding. Next slide. And I didn't want to leave out Spokane because I think they've been dealing with the brunt of this. They have also had their wettest start to the water year on record. Next slide. I pulled out the total moisture percentile from this tool that was developed in part by CERC, Bart Nyssen at the University of Washington. It's run by the Vic hydrologic model, variable infiltration capacity. And this is looking at total moisture, so it's snow water equivalent and also soil moisture. So we're looking at some of the wettest moisture percentiles on record, 100% of normal, not 100% of normal, the 100th percentile. And in Eastern Oregon, it looks dry, but that's kind of hitting in the middle of the range, and they have had a dry week. Next slide. Oh, I have that in there twice. Next slide. Next slide, yes. The NRCS SWE figure wasn't working for me this morning. That's what you get for procrastinating. So I pulled up the current snow depth. We have great mountain snow. We're not too worried about our water resources this year. Some of the lower elevation sites have melted out already. That's not necessarily something to be concerned about, but many of the sites hit their peak before April 1, which is historically the peak of the snow season, although that does have some history behind it. It's when they used to go out and measure all these sites by hand, but most sites hit their peak in March. Next slide. And just quickly, I know I'm running out of time, I wanted to point to why we're not worried about water resources so much this year. We're actually worried about having too much water. These are the reclamation storage reservoirs in southeastern Oregon, and the one in the lower right-hand corner, the Owyhee, was empty, actually empty, during the drought of 2015. It's a 2-year supply, so at 99% full, they've got more water than they need, and they are releasing. Next slide. Briefly, Spokane has been dealing with some flooding issues. I just pulled up the hydrograph from the Spokane River, and looking at gauge height, they were above flood stage in late March into early April for quite a while. Next slide. I just wanted to briefly put up these resources. The slides will be posted on drought.gov, but the top 2 links have been funded in part by the Climate Impacts Research Consortium, and we invite you to check them out and give us some feedback. The Climate Perspective, like I said, is just a fun tool, even though it's in the Southeast. They have a Western piece as well, and then our website. And I'll stop talking. We're going to save questions till the end, but if you have a brief question, we may take it right now. But if not, while Amanda is pulling up the slides, I will introduce our next speaker. It's Mike Murphy. He's a forecaster with the National Weather Service in Pendleton, Oregon, and he's also their climate focal point. And I met Mike a few years ago, in part because he was really interested in getting into some of the climate work in Oregon, and he's been a fantastic partner, both for the DEWS and CERC. So I will let Mike tell us about what we should expect this summer and maybe a little bit more about ENSO.
Okay, yeah, thank you for the great introduction, Kathy. Appreciate that. And hopefully everybody can hear me okay. And yeah, I'm going to be talking about the upcoming outlook for the summer that we can expect and the ENSO outlook. So next slide, please. Okay, so starting out with some of the current ENSO conditions. As you can see in the central Pacific near the date line, we actually have cooler than average temperature, sea surface temperatures over there, but we do have warmer than average sea surface temperatures in the far eastern Pacific, closer to South America. If you look at the bottom graph here, the upper ocean heat content, it's pretty much neutral at this time. We did see a spike, some positive anomalies in March, and then, like I said, fading back to neutral now. Next slide, please. So taking a little bit more detailed look at the different, what's called the Niño regions in the Pacific there, as we showed in the previous slide, the Niño region 4 actually has those below normal sea surface temperatures persisting near the date line, the Central Pacific. And then looking at the typical Niño region, the Niño 3.4 is actually running a little bit above average right now, right around 0.5 degrees above average or so. And then, as I stated earlier, the warmer water is now closer to the South American coast in the Niño 1, 2, and 3 regions, which are running definitely above normal for those sea surface temperatures. Next slide, please. So if we look at what we can expect for the forecast ENSO conditions, this is the CFS V2 model that we look at. And in the upper right there, you can see the graph, and that goes out in time through the summer and into the fall. If you look closely, you can see that the model prediction with some of its ensemble members or earlier and later forecasts, you can see the average is showing it getting up into the El Nino range here pretty shortly in the spring and summer, and then kind of holding steady right near the El Nino threshold, which is 0.5 degrees above average Celsius. And heading into the summer and fall, it starts to trend back upward again. So the CFS V2 is definitely leaning towards developing El Nino through the summer and into the fall. And also, if you look at some of the 3-month water sea surface temperature anomaly maps on the left-hand side there, you can see that the Pacific Ocean is generally above average water temperatures, is what the model is predicting through the summer months. And looking out at the last image there for October, November, December, it definitely takes on the typical El Nino look to it. So, okay, next slide. So looking at some of the plume models of the forecast ENSO conditions, again, through the upcoming fall here, and this is from the IRI and CPC, all the different models that they have. You can see in yellow there, a little bit hard to see within the plume, but the thick yellow line there is what's called the dynamical model average. And that's running a little bit higher. It's leaning more towards the El Nino development heading into the summer and fall. Whereas the light green line, but I guess the thick green line, yeah, right there, that's the statistical model average, and that's running pretty much right on the El Nino threshold heading through the summer and fall at 0.5 degrees above average. So overall, looks like the models are leaning towards a possible El Nino. Actually, next slide, please. As you can see here, like I started to say, the models are leaning towards an El Nino, but really right now, it's only slightly favored. So you can see as we head into beyond August, September, October, November, it's right around a 50 to 55% probability of El Nino, and then about a 40% chance of it being neutral still, and only about a 10 to 15% chance of La Nina. So as it says there on the bottom, we have ENSO neutral conditions right now, but we are expecting increasing chances for El Nino development by the late summer and fall. Next slide, please. I wanted to show this really quick. I know Kathy really hit on this already, but obviously, unless you've been living under a rock, it's been cool and very wet for the past 3 months. It's been cool and wet, so what can we expect coming up for the spring and summer? So next slide, please. So yeah, looking into May, April's been pretty wet and cool across the area. Heading into May, we think the pattern is only going to slowly start to change. The Climate Prediction Center is forecasting equal chances for above, below, or near normal temperatures across Washington, Oregon, and into Idaho. That's on the left-hand side. Then the precipitation on the right side is showing that we might start to dry out a little bit. Kind of just, instead of the super wet pattern we've been in, we might be more heading back towards equal chances for that above, below, or near normal precipitation. It still does look a little bit wet, or the odds are tilting towards a little bit wetter month for northern Idaho. Next slide, please. And then if we take a look at the 3-month outlook, which encompasses May, June, and July, you can see the temperatures on the left-hand side there. They are starting to favor above normal temperatures. And as we saw, May was equal chances, so probably most of this above normal temperatures would be more towards June and July, is what the Climate Prediction Center is thinking. And then if you look at precipitation, we're still looking at those equal chances for above, below, and near normal precipitation. So nothing's really standing out. There's no strong climate signal to indicate that we're going to continue to see a very wet pattern or a very dry pattern. Just probably pretty close to normal is what we're expecting for precipitation in the late spring into the early summer. Next slide, please. I wanted to show this. This is the 3-month outlook for June, July, and August, so the heart of summer here. You can see that the odds continue to increase across Oregon, Washington, and Idaho for those above average temperatures. So the Climate Prediction Center is seeing indications that temperatures could be running above normal as we head into the heart of summer there. But precipitation, this is a bit of a change. They've transitioned back to just equal chances, so it could be pretty close to normal precipitation across the area for the summer months. I think earlier they had indicated kind of a dry bullseye over the area, so seeing a little bit different climate signal developing there for the precipitation. Next slide, please. And then as we head in towards the latter half of summer and into the fall for July, August, and September, the Climate Prediction Center is favoring even higher odds for above normal temperatures across the area. So I think it's really going to be a situation where we slowly transition out of this cool and wet pattern, heading into the late spring, and then gradually getting warmer and warmer, with perhaps some of the warmest temperatures of the summer occurring in that July, August period, maybe lingering into September. And then if you look on the precipitation on the right-hand side, again, really no strong climate signals for most of our area, but looks like it is going to be wet over the Rocky Mountains and perhaps extending back into portions of Idaho as well. Okay, next slide, please. So we kind of hit on what we can expect as far as the seasonal outlooks here. And as Kathy already mentioned, it's been extremely wet across the area. We're not dealing with any drought really right now for the first time in a while across Oregon, Washington, and Idaho. And this is the Climate Prediction Center's seasonal drought outlook, which is through the end of July. And as expected, we're not really looking for any drought development across our area. So some pretty good news there. And next slide. So that is all I have for you guys today. I guess we're going to hold off on questions or comments until the end of the webinar. So thank you very much. And I'll mention that my data and graphics came from the NOAA Climate Prediction Center, IRI, and climate.gov. So thank you.
Great, thank you, Mike. For those of us who dislike hot summers, that's not great news, but I guess that's the way things have been going. Next up is Roy Sando. He's with the USGS Water Science Center in Montana and Wyoming. And one of our DEWS partners reached out to me after seeing a presentation of his and said he'd give a great webinar update. And luckily at that time I was planning this webinar. So we're really excited to have him join us. And Roy, I'll let you take it from there.
Yeah, thanks, Kathy. The name of this project is Probability of Stream Flow Permanence, and the work is funded by the Northwest Climate Science Center. And that shortens into PROSPER. So that's the acronym I'm going to be using throughout this presentation. So generally, people understand, that stream flow conditions fluctuate and that they're highly dependent on annual conditions like snowpack and temperature and that kind of thing. And furthermore, stream flow permanence can fluctuate too. So the location and length of perennial streams, particularly in mountainous headwater catchments. But what a lot of people don't realize is that currently our most nationally consistent and prolific data set that's used to quantify a lot of these stream flow permanence classes is the NHD and or the National Hydrography Data Set. And that data is largely based upon these field campaigns that were conducted back in the early to mid 20th century. And so the intermittent and perennial designations on those data sets is based on these one-time snapshots that these field crews went out and made. And so because of that, our team recognized the need to update that. And so the objectives of our work, the PROSPER objectives, are to go from these static one-time snapshots of essentially yes or no for stream flow permanence to annual high resolution probabilities. So every year you get at 30-meter resolution a probability that that location is going to have year-round stream flow or not. So our study area, which I'm sure everyone here is pretty familiar with, is the Pacific Northwest, and specifically the United States portion. What we're using to calibrate our models are these stream flow permanence observations, and these are observations that were made on the landscape that we're processing into essentially wet or dry during the low flow period. And we've got about 24,000 observations. Yeah, and so we're using these to link up to basin characteristics to develop models to predict this across the region. So this is what those 24,000 observations look like across the Pacific Northwest. So then the basin characteristics, or the predictor variables that we're using to describe this at sites that we don't have observations for, consist of 294 predictor variables. And this is largely because we have a high number of climatic variables, like precipitation, snow water equivalent, temperature, that kind of thing. And we've got annual or subannual values for those. So, and we needed to do this so that we would have predictions for every year, not just, a one-time snapshot or average conditions. And we're formatting these into something called a continuous parameter grid. And because that's so important, I'm just going to give you a quick example in a small basin. So here's what the derived stream network looks like when you just take an elevation grid and derive, your flow accumulation. And traditionally, if you wanted to understand what's going on in a basin, you'd have to go and delineate your basin and then go and get your basin characteristics. But with these CPGs, or continuous parameter grids, we eliminate that. So instead of just discrete basins, what we're able to do is get values for each basin at every 30-meter pixel. So here you're looking at an example of a CPG that represents snow water equivalent on March 1st of 2008. And again, every single one of these pixels represents the average snow water equivalent on that day for all the upstream area. And so I'll just run you through the runoff season for 2008 to give you an idea of what these look like. And you can kind of start to see how the stream flow characteristics might fall out of this. So again, back up to March 1st. And to give a quick example of how powerful this is, so we use parallel processing to retain this high spatial resolution that lets us get at the local scale accuracy across the entire region. So again, these are 30-meter pixels representing the upstream average across the entire Pacific Northwest. And so this is just one of those 294 grids. And we'll have 294 grids. We link those up to our stream flow permanence observations. And we've developed a random forest classification model. And so once we analyze the cross-validation of that, we're getting about 79% accuracy. And you can kind of see where it's working, where it's not. But again, we want this to be regionally consistent. And so this is sort of a regional model for the first go around. And so I just want to give you guys a quick look at what the output of the PROSPER work looks like. So I'm going to focus in on the Boise River Basin in central Idaho here, and just show you again what these probabilities look like. And for visualization, I binned them into essentially low, medium, and high probability of stream flow permanence. So you see the red pixels, which have a low probability. Green are kind of those transition zones, and then blue are the high probability of year-round flow. And 2011 was generally a wet year in the West. So you see there's quite a bit of blue here, a little bit of green, and then not too much red. But when you look at 2015, which was a really dry year, you can see the expansion of those dry predictions and then the shrinkage of those wet predictions. So again, 2011 was a wet year. 2015 was a dry year. And so you can start to kind of get the idea of how we can capture the interannual variability in these conditions across the region. So to kind of pound into people's heads the idea that perennial streams and intermittent streams are not these well-defined segments, but rather fluctuate and are dynamic systems that depend on the annual conditions, I'm just going to run you through our annual predictions from 2004 to 2016 for the Boise River Basin. So here's 2004. Again, the blue are high probability, the red are low probability, and then the black are the transition zones. So you can really start to see the dry years that fall out and the wet years that fall out. And then 2016. So another way to look at that is just the frequency of dry predictions versus wet predictions. So here you're looking at pixels that represent the number of years that were predicted to be dry. So the darker the red, the more often or the more frequent that pixel is predicted to be dry. And then the pink, the lighter the red, those are spots that are predicted to be dry, but not all the time. And on the other end of the spectrum, the darker the blue is the more often that pixel is predicted to be wet or have year-round flow. And then the same thing with the light blue, just predicted to be wet, but not as frequently. And one thing that's pretty cool we think about this is that we're not including any indirect variables, so like drainage area or elevation or anything like that. But using the hydrologic variables, we're still able to capture that stability in the larger streams and predict them to be perennial almost all the time. So there are some limitations with the Prosper model, namely that they are intended to capture natural systems. So we're not including dams or regulation. And so where there is impoundments or artificial storage, there's most likely going to be a more stable system there and more often perennial flow. But our output captures what happens under natural conditions. Additionally, we're sure that there's variability that goes on that's more localized in what we're capturing. But just a qualitative look at our data kind of indicates that about 1 kilometer is what is appropriate for this model. So if you go out to the landscape and pick out a specific spot, there's a good chance that we might not capture exactly what's going on there, or that the model parameters aren't appropriate. But hopefully within 1 kilometer of that, we'll get to be close. So the products that are coming out of this work, we're going to be publishing those 24,000 streamflow permanence observations. Additionally, all the 294 continuous parameter grids, which we're hoping can be used for much more than just predicting streamflow permanence, are going to be published. And then finally, the probability grids that I showed for the Boise River Basin, those will be published again at 30-meter resolution across the entire Pacific Northwest. And we're hoping that that'll be done towards the end of summer, early fall. So our contact info is there. Feel free to call or email with any questions you guys might have.
Great, thank you so much, Roy. That's really interesting work, and I believe you will be on the Oregon State campus in May giving a longer version of this presentation for those of you who are local. Now I'm going to turn it over to the coordinator of the Northwest USDA Climate Hub, Holly Prendeville, and Holly has been really enthusiastic and really a key player in putting these webinars together. It's one of the reasons we keep going. So we're really happy to have her on board, and she's going to give us a quick update on the hubs and then introduce our last speaker.
Thank you, Kathy. As Kathy said, I'm Holly Prendeville. I'm the coordinator of the USDA Northwest Climate Hub, and we communicate science-based climate information and tools so that land managers have this information and tools to help them manage their lands. If you haven't been to our website, I suggest visiting it. You probably have a variety of questions after hearing the climate outlooks, and so you can view the vulnerability assessments, there's educational resources, as well as a variety of decision support systems. One tool to highlight is the seed lot selection tool, assisting foresters to choose the appropriate seed lot or plant material from where it should come from in their restoration efforts. You can see the link here, and if you just want to follow the hubs in general, all of the national hubs are on this one Twitter site, so you can follow us there. Next slide, please. The Northwest Climate Hub partners with NOAA and NIDIS to bring in speakers on these webinars, and today it is my pleasure to introduce Karen Launchbaugh, sorry Karen, who is the professor at the Department of Forest, Rangeland, and Fire Sciences at the University of Idaho, as well as the director of the University of Idaho's Rangeland Center. And today, Karen will be speaking to us about targeted grazing to manage annual grasses and wildland fuels. On to Karen. Thank you.
Can you see my screen? I'm sorry, I just got off mute, and hopefully you'll be able to see what I see, which is a slide on targeted grazing, right?
Yes. Yes.
Excellent. Okay. Well, thank you so much for the invitation. I've already learned a lot, and I appreciate the fact that one of the biggest challenges that rangeland managers have to deal with every year is just knowing how much forage there is out there, or if water is going to be available in streams. So although I'm going to be talking about grazing and annual grasses, the topics related to climate and climate variability are super important. So I'm director of the Rangeland Center, and our motto is science and solutions for the range. So we are part scientists. There's 25 researchers and educators here at the University of Idaho that work on almost every aspect of range, from grazing to succession to fire to climate. And then we're partnered with people out in agencies and organizations. So anything that we do in the Rangeland Center is a bit of science and a bit of solutions. And one of the topics that we've been working, several of us have been working on, is how grazing is used to manage annual grasslands. I'll also say that I'm one of the officers or past officers of the Targeted Grazing Committee in the Society for Range Management. So I will give you some information on that also. So let's talk a little bit about how all of these climate variables might play out on rangelands that are dominated by annual grasses. Okay, no doubt that one of the biggest challenges we're dealing with in the West and in the Pacific Northwest is larger fires. Here's some data from the Interagency Fire Center that if you look over time, last 20 years or so, what you see is just a really clear trend that the number of fires is going down, but the area those fires are covering is going up. So we're always in an effort to try to reduce that size of fires and to try to minimize that size and number. And this is really important to me in Idaho, because if you look at this graph, there's a red dot for every fire that was over 300 acres. This is between 1970 and 2007, but the picture is the same, and you can see that big red splotch right around the Snake River Plains. We really are the center of fires on the range. So we at the Rangeland Center work a lot on this topic. And of course, if you know that part of the Snake River Plains, cheatgrass and invasive annual grasses are really quite a big problem, and probably a pretty big contribution to why we see so much red on this map right there. Okay, so there's a lot of things that have changed over time, and reason that we're having these bigger, larger fires. One, a lot of people would recognize that the number of livestock and the grazing pressure on the land has gone down, especially around the 50s when the Bureau of Land Management came along and the Forest Service started issuing permits and regulating grazing. We had really radical reductions in grazing. And then in recent years, with environmental concerns, numbers have gone down. So no doubt there's less livestock eating forage, which may reduce the fuels. But there are a lot of other things that are going on. More human development, more use of roads out in the range and annual grasslands. Of course, annual grasses came in the about 1950 or so. We started seeing increases in cheatgrass and other annual grasses. And then along with this, especially in recent years, longer, hotter, drier summers, which have really contributed to this problem. So all of these things combined are creating a situation where we have a lot of annual grasses, and they're in places that are experiencing long, hot, dry summers, and in places where there's a lot of human activity. So that's why we're seeing, at least in the Snake River Plains and in much of Idaho, an increasing number of fires. Okay, so what could grazing do to affect that wildland fuel and fire topic? Well, you can see from this picture, and this is just a classic picture, you often see this where there's a fire that goes along and it burns to a fence and stops. And that's because the area on the right-hand side of the fence was grazed and the area on the left was not. So one thing we know that grazing can do is to affect the perimeter or the extent of the fire. More importantly, though, probably is that grazing can also often be used to make the fire more patchy. And so rangelands, even sagebrush, which is not adapted to fire, sagebrush ecosystems are adapted to fire as long as the fire is patchy. Another thing that we're learning recently is grazed ecosystems tend to experience less intense fires, so less fires that aren't as hot, which again plays into the recovery of those ecosystems after fire. Some of the data I'll show you that we've been doing is looking at flame length and rate of spread, because those are important when you're fighting fire. So where does livestock grazing fit in? I'm going to talk mostly about annual grasses and how we might control those, but herbaceous fuel amount is also being studied and examined on rangelands. Let's focus on annual grasses. Of course, when I say annual grasses, I'm talking mostly about cheatgrass or downy brome, which is Bromus tectorum. Medusa head is also a big problem. Red brome, especially in parts of Nevada, not so much in the Pacific Northwest, but red brome is a problem also in areas. The issue is that it's a very flammable fuel. It's easily ignited, and the other thing about these annual grasses is they've extended the fire season because they mature earlier, so the fire season starts earlier, and we have longer fire seasons and a quicker return interval. Okay, so start there. We've known for quite a long time, in this study in 2003 by Jay Davidson out of Nevada, just as a good example, we know that you can graze cheatgrass and downy brome, and you can really suppress it. So this was a study where he was using sheep, 2000, 2001, 2002, you see those gold bars. When sheep are grazing, there's way less cheatgrass in the ecosystem than if you weren't grazing it, or the gray bars, which are the control. The problem is, if you stop grazing, as they did in 2002, all bets are off. Cheatgrass is a really adaptable plant, and so if you still have seed in the seed bed, it'll come right back. So they stopped grazing in 2002 after 3 years, and the cheatgrass was back to what it would have been before. Okay, so that goes to the next point, which is this was a spring grazing study, and we know that the timing of grazing is the key. So just as a graphic, in cheatgrass-related areas, almost all plants are palatable, the blue line, when they're young, and they just become less and less palatable as the season goes on because they become more and more fibrous. But plants are really only susceptible, I'm talking mostly grasses and forbs here, but they're really most susceptible to grazing at seed set. So the challenge with targeted grazing to control a plant is to find a time when the plant is palatable, but also susceptible to grazing. And on rangelands, if you think of annual grasses, they start in the season earlier. They're still very palatable, and they start before the native plants come on. So there is a sweet spot kind of right in the middle here where annual grasses are still palatable and susceptible to grazing, but that comes at a time before the native perennials are susceptible. So the timing is important to graze those annual grasses before the perennial grasses come on. I'm going to switch gears a little bit. This is because though timing, we're usually thinking of it as being important right before the perennial grasses come on. There's some really interesting work coming out of Nevada now that says we can really use grazing in the winter or the late fall as a tool for cheatgrass. So in this study that was done in 2007 to 2009, they grazed in September, and they found the cheatgrass in the grazed areas went down, whereas the cheatgrass in the ungrazed areas, it changed from year to year, but over the period of this study stayed about the same. What's intriguing is that during that time, that winter grazing caused an increase in perennial grasses. It was apparently a good in both the grazed and ungrazed regions because the perennial grasses went up in both of those sites. But we certainly saw a much greater increase in the grazed areas. Okay, why this is important for climate and understanding climate is because winter grazing is easy because we know how much biomass is out there, so we know how many livestock can be used to reduce that fuel load. And we're also not at risk of the plants growing back after grazing. So winter grazing is something that we're just starting to work with, and the folks out of Nevada are really kind of leading the way on that. Switch gears to Medusa head just to let you know that the story is roughly the same. This was some work out of California where Medusa head's quite a problem. And in both of these situations, grazed in March and or in the left bars and or on the right bars in June. In both cases, the grazed sites had less Medusa head than the not grazed sites. If you dig into this data a little bit closer by Di Tommaso and others in California, what you see is that the timing is important. In this case, ungrazed is the leftmost bar, and then if they're looking at grazing at March, which did decrease Medusa head on 2 different sites, but it looks like March or April and May is really a time when grazing is early enough in the season to still let those perennials, if they're there, continue on, but also is a time when it's pretty detrimental to Medusa head. One last study, this is kind of way out of our region, northern Arizona, but I think the point is common to many of our regions. And what we see here is the bar, this bar that I kind of drew a pink line on, the bottom bar from 97 to 2004 was an area that was moderately grazed. And what I'm depicting here is the abundance or occurrence of cheatgrass. So that a moderately grazed site had less cheatgrass than a heavily grazed site, what is called the high impact site here, or then no grazing at all. The blue line is no grazing at all. And so I think this, from what I see in the field, there's not a lot of data on this, but lightly or carefully grazed pastures tend to have less cheatgrass than ungrazed pastures. The problem is if you have very heavy grazing, especially what happened here was 2002 was a drought. So heavy grazing during drought can really expand cheatgrass abundance. So there's a sweet spot where there's some grazing at the right time, at the right intensity that really might keep cheatgrass at bay. So bottom line, take-home messages: if you have no grazing at all on the left-hand side here, cheatgrass will probably increase to its ecological potential for the site. Spring grazing before the perennial grasses or perennial forages come on will likely decrease the abundance of cheatgrass as long as you get off of that site before the perennial grasses start to flower. If you start grazing at that time, at the time when grasses flower, there's some old data from the Great Basin that shows that you damage the perennial grasses and the cheatgrass is released from competition and tends to do fairly well. And now this new data out of Nevada that says even dormant season grazing in the winter may be important to reduce cheatgrass. So the answer to the question, is grazing a way to reduce cheatgrass? The answer is yes and no. It really depends on the season. So the last point I want to make, so this is all really cool that we can control cheatgrass, but how does that affect fire behavior? There was a really nice study done in Nevada by Diamond and others. And if you can kind of think about this fire coming from the left-hand side of this graph, and they were measuring flame length, and right before they got to the treatments, the flame length was the same. When they got to the treatments, areas that had been grazed are the gray bars, and right as soon as that fire hit the perimeter of the treatment, the flame length was decreased. So 5 meters, 15 meters, 35 meters, and 55 meters inside of the exposure showed a real reduction in flame length. Whereas the area that wasn't grazed, of course, flame length decreased across that, or increased across that site. The reason that's important is because it shows that grazing does affect flame height, and reducing flame height or flame length is important if you're thinking about direct attack on fires with firefighters. So this was a really heavily infested site. It was quite heavily grazed. This was a fall burn, so it may not be particularly native conditions, but it certainly was effective. If you want to learn more about this, there's a really great article, or there's a really great document out by ebipm.org, which is ecologically based integrated pest management.org, and the guide is called the Green and Brown Guide, which talks about what do you look for in terms of timing of grazing. So what do we really know? Grazing can reduce fuels. We know that grazing will not stop fires, especially under extreme weather conditions. So the best grazing in the world is not going to stop a fire if it's really hot and dry. Grazing can reduce cheatgrass. Grazing can increase cheatgrass. The key is in the timing and the application. And finally, grazing can reduce fire intensity and promote recovery after fire. So if you want to learn more about this and other topics, including webinars on the topic, go to targetedgrazing.wordpress.com. That is the website for the Targeted Grazing Committee of the Society for Range Management. You can find me at range@uidaho.edu, and hopefully you'll come to the Rangeland Center website sometime. So thank you very much. That's my story, and I'm sticking to it.
Great, thank you, Karen. So we have about 10 minutes for questions for any of the panelists, and to ask them, go into the question box and type it, and Amanda and I will monitor this box. And while you're thinking of questions or typing your questions, we wanted to remind you that we do these webinars regardless of what the climate situation is, drought, not drought, flooding, every 2 months. So the next one will be in June on the 26th at this same time, 11 a.m. Pacific time. And we really tailor these things to what's going on, but we like to highlight research and some interesting tidbits as well. So if you have any ideas or you want to present, feel free to either reach out to myself or Amanda. So we have a question for Roy. It says, does the modeling capture variation in demand well, say from agriculture?
Yeah, so that was one of the variables that we included, and we included the land cover data set, national land cover data set. So we put in like developed agriculture. We try to get irrigation from just irrigated acres, that kind of thing. What we found was that generally, because we're targeting the headwater areas or the mountainous regions, or that's where a lot of these streams come from, the effect of agriculture on stream flow permanence was so minimal compared to these natural drivers that it really didn't fall out that well. So we tried to do that, but what we found is that that's just such a specific occurrence that it really wasn't that impactful. So I would say no overall.
Great. Thanks. We have another question. It's for Karen. Do you have any ground temperature data for some of the flame height data? I'm interested in heat generated to support generation of fire-induced changes. He's thinking of protection of fire crews and fire spread ice.
Great question. I don't have it for the data that I presented, but there are people that have collected the heat data. I'd recommend that you visit or you look up April Hewlett at uidaho.edu. So that's April H at uidaho.edu. She works very closely with the ARS lab at Burns. So the ARS folks in Burns have measured the temperature of soils and vegetation as fires go across them and related it to flame height, as has April Hewlett. So sorry, I don't have it, but it does exist. I wouldn't say there's a lot of it, but we're starting to put the pieces together to think about fire intensity, flame height, and those questions. So sorry, I don't have a perfect answer.
Great, thank you. I'm not seeing any other questions, but we'll give folks, yes, here's one. I talk a bit about the predictive value of his work and whether it might be of use for fishery managers who want to target areas where fish stranding might be likely. Is there a chance this could be made operational so that daily snowpack and other conditions would give a running prediction of stranding potential?
Yeah, definitely. And that was one of the motivations for getting this work off the ground. And specifically, so we were working with Trout Unlimited. I don't know if you saw on the first slide there, but they're one of our cooperators on this. And originally we were planning on doing just like a one-time average conditions kind of output, excuse me. But our colleague from Trout Unlimited had said, well, it'd be really great if we could get annual predictions because of just that. We need to know where this connectivity is available for fish to migrate to or potentially be stranded. So right now we're just trying to get the foundation laid to get this modeling out there. But the goal is definitely to develop the model so that, say, in like April or March or May or something like that, you can check the conditions and see, you know, what the probability is for, say, August or you know, the low flow period. So yeah, that's definitely the goal, and we're hoping to get there in the next couple of years.
Great, thank you. I'm not, oh, yeah. General question for the group. Low and high thresholds can be variable depending on audience and scope of work. For instance, sometimes below 30% is below normal and sometimes below 40%. Is this a problem in terms of messaging, regardless of the scientific probabilistic justification? So Mike, I'll punt this to you and I can back you up if you'd like.
Okay, sure. Well, I'd say I think for our climate outlooks, we use the 50th percentile as below or above normal. But I see what you're saying because there is kind of that area in the middle where it's near normal. But I would say, yeah, we should probably try to be consistent, but I'm not sure how much of a problem that's been. So I'm not sure.
And this is Kathy. I think those of us who work with these outlooks and communicate them to resource managers and the public, really have a difficult time with the tertiles because most humans think in terms of a coin flip, myself included, and these are really binned into 3 areas. So that equal chances really encompasses the entire spread and isn't just average. Yeah, so when we say low or below normal, and it's actually not statistically significant in terms of how other people may think, it's certainly communications issues. And I know folks have been struggling with this throughout time.
And I want to also add that the Climate Prediction Center actually does do a experimental 2-class system too. So if you want to email me or whatever, I can get you to the link to that, which is more cut and dry. Is it going to be above or below? So they do have that as well.
Okay, I think that's it for questions. Again, thank you to our panelists, thank you to our attendees. Huge thanks to Amanda and Kathy Bogan, who's silent behind the scenes, but helping out. She's at the NIDIS program office. We couldn't do these without participation both from our speakers and our attendees. So I will let you on, those of you on Pacific time, go to lunch, and the rest of you go about your day, and thank you very much.
Yeah, thanks so much, Kathy.
Yes, thank you to all our speakers for joining us today.
But my pleasure.
Thanks. We'll see you guys.